Alrighty, let's get started. Okay, so sorry for the recording, it's a little low. My little tripod thing broke. It broke in shear. Funny thing. So you'll see a little bit of my textbook. That's the best we'll get. So welcome to lecture 18. Last week before final, right? We're going over chapter 8. All content is from Munson 9th edition. And I thought we would do lecture first because I felt bad for the first group that went last week. People kept trickling in. And, I get it. It's early. So I thought I'd rather have them come late on me than yours presentation. So we're going to do lecture first. Got not a decent amount to cover, but I want to have enough time for presentations. So we'll get through this and then have enough time for presentations. So agenda today. We have one more chapter 8 example that covers both major and minor head loss. Right, last time we did major head loss for turbulent and laminar flow. Here we have another turbulent, but we have a minor head loss, right, for the fittings and the diameter cross-section differences. And then I have another slide just to go over other equations to know for homework. I went through your homework. We basically will have covered everything you need to do the homework. But there's just some minor equations you might need to solve the problems. And then after that, we'll do presentations, course evaluations. I'll talk about homework 7 quiz on next Monday. And then announcements, right? We have quiz on Monday and then final exam next Wednesday. So I hope we'll have enough time for these bullet points here, but these are our priority. So if we run out of time, I'll make an announcement about this stuff. Okay? Okay. Sure we're recording, testing. Okay. So I have some quick review slides to make our example problem make more sense. So for viscosity, we went over what dynamic and kinematic viscosity is. Right, so dynamic is more what you think of viscosity is, which is the thickness of the fluid. Kinematic viscosity is more under the impression of gravity. And we have this equation nu, right, which equals the dynamic viscosity divided by density. And the main reason why we have this is you can plug this into Reynolds number and get a different Reynolds equation. So sometimes on homework or exams, I'm going to give this nu instead. And then you're going to see, oh, there's no mu or rho. What do I do? This is the conversion to that. Okay. Minor losses, right? This is mainly due to fittings or changes in cross-sectional area, right? So the main thing, this KL is a loss coefficient. You get that from either the type of fitting you have. That's going to be on a table. You can get that through a graph, which is the change in cross-sectional areas, which I'll show you, right? V is velocity and G is gravity. Okay, we already went over this. I just kind of wanted to remind you. Minor loss coefficient, so this is the other KL. So if you have your cross-sectional area changing in your flow, right? If you go from a bigger area to a smaller area, you take the ratio and follow this graph to get your KL there. Here's the inverse, a smaller area to a larger area. You follow this graph to get your KL. I have an example that we're going to go through to do that. And you'll see in the example, if you have multiple KLs, you're actually going to take the sum of the KLs, assuming your velocity is the same for your whole flow. Okay, so here's a table what you would probably need for your KL fittings. And we're actually going to use this in the example. I just wanted to show you, right? So you have your elbows, 180 return bends, T's, union threaded. So they'll state in the problem what your fitting is, and then you grab the KL from here, and you plug it into the proper equation. Okay, so this is all review. We already went through this. Major head loss, right? We did major head loss already, but this is the equation for it. You mainly will need this one on the very right here, but if you need it in terms of specific weight, this gamma, right, that's just rho times G, you have it there. And the main difference, right, of laminar flow and turbulent flow is how you get this friction factor. So laminar flow is just 64 divided by Reynolds number, And then if it's turbulent flow, you have the Moody chart, right? So this is the equations for the Moody chart, or you can go to the actual chart yourself. Okay, so we already went over this. Here is your Moody chart. And here's the table for your equivalent roughness, right, your epsilon. So you have, when you use this chart, you get your Reynolds number, rho VD over mu, or you use that conversion I showed you, right, for kinematic viscosity. You could do that Reynolds number 2 down here. And then you solve for your epsilon over d. You find your epsilon here. So you find your Reynolds number, you find the right curve, and then you find your friction factor. We did that last class. I'm going to do it one more time in the next example this class as well. All right, this is important. Like I said, I'm kind of leaning towards having this kind of exercise, something with your quiz or final. It's going to pop up in one of those two. Okay, so since we just reviewed those concepts, we're going to go over a problem here that kind of covers everything, which is why I like this one. So we're going to talk about major head loss and minor head loss all in one problem. So let's read it first for the video, and then I'll move it to the whiteboard over there. So water flows steadily through a 0.75 inch diameter. So that means this is this diameter here. Okay. Once it gets to this, you see that it changes to 0.6 inch diameter. So it gets smaller, right? So that's going to be our KL that you can kind of already see. Galvanized iron pipe systems, right? Keep in mind this material. And it's coming at a rate of 0.02 feet cubed per second, right? That's your flow rate, your Q. Your boss suggests that the friction losses in a straight pipe are negligible compared to the losses in the threaded elbows and fittings in the system. So that sentence is basically summarizing, your boss thinks the major head loss in the friction of the pipe is negligible compared to the minor head losses in the fittings. So we'll have an answer to that, but mainly we're just comparing what we get for major head loss and minor head loss. Okay, then it asks, do you agree or disagree with your boss? Support your answer with appropriate calculations. Okay, so that's what we're going to do. Feel free to read the problem over while I write our givens and stuff. Stand this side. Okay, here we go. So, okay, given. Right, we're gonna steal a little thing from Dr. Bridge and use the FOS figure as shown, because I don't want to redraw everything and write all those dimensions. Some things that we're gonna want is diameter 1 is equal to 0.75 inches. I'm calling diameter 1 just this diameter that goes along this bend here. That's 0.75. Diameter 2 is going to equal the 0.60 inches. That is this diameter right here. Okay. Now we want to find, basically compare major to minor head loss. And we can give an answer to our boss to that problem once we compare them anyways. Okay, assume we're assuming a viscous pipe flow, right? Because that's kind of our big thing in chapter 8. And can someone tell me from our first midterm, right, if this comes up again in the final, if the flow is viscous, what does that mean in terms of stress in your fluid? Shear stress, yes. And is it 0 or not 0? Not 0, correct. So if there's viscous pipe flow, if your fluid is viscous, that means shear stress is no longer 0 compared to the other problems that we've been doing. Okay, so in my notes I have parentheses, shear stress is applied, but I already explained that, right? And I'm giving you this new, right? And this is kinematic viscosity, so 1.21 times 10 to the negative 5 feet squared seconds. Okay, think that's everything. So, do solution. Okay, any questions before we start for problem setup? Let me check something really quickly before we start. Okay, I'm just making sure I have the right units for kinematic viscosity. So it's length squared divided by seconds. So that's good. Okay. Okay, so like I said, right, whenever we solve problems, I hope you kind of have this mindset when you solve them in the future. You always want to kind of work backwards of what you want to find and see how to get there. So like I said, compare major to minor head loss. So first let's do head loss major, because this is the one we practiced already last lecture. So right, that equation is just friction factor, length divided by diameter, v squared divided by 2g. Okay, then let's kind of go through this, right? What do we have, what do we don't have? Friction factor, do we have yet? No. Awesome. Length, do we have? Yeah, right? So let's push our problem solving a little bit, right? If something like this pops up on your exam and you got to figure things out, can someone tell me, based off this picture, what would they do for length? Just guess. No hurt in guessing, right?
11 inches.
What was that?
11 inches.
11 inches. You got...
Oh, sorry, not 11. There's another 6 in there.
Yep, 6.
So that would be what? 6, 12, 16, 17 inches?
Yes, thank you. So how Ryan got that right, 6 plus 6 plus 4 plus 1. Okay, that is L. So I will write that. Okay, so L is equal to 6 plus 6. I'll do 6 plus 6 plus 4 plus 1. It's the same here. Yeah, so 11 inches. Okay. Oh, sorry. You're right, 17 inches, not 11. Okay. 6, 12, 16, 17. Okay. And right, for housekeeping, I just like to rewrite the variable. And because, right, if you're solving your problem, you don't want to look through this and find it. I just like to rewrite it and underline it here. Yes?
Looking at the picture, it kind of looks like there's 2 diameters, like the 0.6 inch diameter is consistent across the 1 inch.
Right.
Which would make me think you would need to do 2 HL majors because there's 2 different diameters.
2 HL majors.
These, each of the HL majors have diameter in them.
Right.
And then add those up separately.
That's a... So the one thing is it's at the very end, but it does taper off. So you'll see once we solve the problem, we account for this difference in diameter with our HL minor. But yes, you bring up a good point. Realistically, that might have a small factor. For the sake of this problem, for simplicity, we're just gonna ignore that. Okay. We're gonna assume that our length is just throughout this whole length of 6 plus 6 plus 4 plus 1. Yeah, that's a good point to make as well, though. Okay, so, right, we have L, right, we have D. Do we have velocity? If not, does anyone know where we can get velocity from? Q, which is AV, awesome. Q equals AV. So Q equal to AV, right? So we have V equals A over Q. Oh, sorry, Q over A. Q over A. Okay, what is our Q? Did I not write that in our givens? I have that already here. Yeah, so forgot to write that, but Q over here is 0.02 feet cubed per second. Okay. Okay, so then area, right, that's just pi over 4, 0.75 inches. Do a conversion to inches to feet. That's going to be squared. And then your velocity is going to equal 6.52. Let's make this a little bit neater. 6.52 feet per second. Okay. Okay, so we have V, right? We have G already. We know that. So now the only thing left is friction factor, right? Okay. So when you see friction factor, you have to determine what approach to take, right? Laminar flow approach or the turbulent flow approach. How do we know which one to take? What should we do first? Reynolds number. Okay, that's very important for final, right? Reynolds number. So Reynolds number is equal to rho VD over mu. You use the conversion that I showed you of nu, right? We pointed out last class, Henry pointed out, this might be confusing. V and nu are different, right? So don't get those V's confused. I just try to have this little dash line on the top of the V to make it different. Okay, rho. So that means RE is equal to VD over nu. Okay, so this is 6.52 feet per second. Diameter is 0.75 inch divided by 12 to get to feet, right? I don't know why I keep doing this in my solution. You could just convert in the beginning and plug it in. That might be probably easier, but that's just how I'm doing it. Okay, and this is all divided by nu, which is, I gave to you, right, 1.21 times 10 to the negative 5 feet squared over seconds squared. Okay, and if I don't give these to you, they're in the table, right, for chapter 1. But in finals and exams, I don't think I'm going to have you waste too much time finding them in a table. I'm probably just going to give it to you. Okay, so the Reynolds number for this that I got ended up being 33,677.7. Another way to write it that's more graph friendly when we use our graph is okay, someone remember if this is going to be turbulent or laminar? Turbulent, right? Because this is greater than 4,000. So, okay, so turbulent. Okay, so now that we know it's turbulent flow, what does that mean? What do we do?
Use the Moody chart.
Moody chart, perfect. Thank you. So, and before we go to Moody chart, right, you need this epsilon because that's what you need for the Moody chart. And if you look at our problem, it says galvanized iron. Galvanized iron's right here. Okay, 0.0005. So, all right, epsilon is equal to 0.005. Okay. And then we need epsilon over d, right? So epsilon over d, I got to be 8 times 10 to the negative 3, or to be nice to our chart, it's 0.008. Okay, so let me underline what we need to get our friction factor, right? We have Reynolds number, and we have epsilon over d. Okay, so this had me to think about a little bit last night. You'll see in our axis here, they have, at the 2's, there's a 10 to the something power. I would ignore that. You don't double it. You don't go, oh, this is 10 to the third, and this is also 10 to the third. They're just showing in parentheses, this is what it would look like if you apply it to the 2. Yeah, because it's not going to be 2 times 10 to the 6th power. That's way too much, right? So anyways, what I'm just saying, if you see these little 10 to the something power next to the 2's, you just kind of ignore them. They're just trying to show you that this range is 10 to the whatever power. Okay, so let's run through the example. Reynolds number was 3.37 times 10 to the 4th. So 10 to the 4th is right here, right? So 3.37. If 2 is here, right, you can kind of count these dash marks. 3 is going to be closer to this end. So 3.37, okay? And then you find your epsilon over d, because you're going to go up to that curve, right? Epsilon over d is right here. We got 0.008. So this curve you follow. This Reynolds number you follow, right? It stops right here. And you follow that all the way to your friction factor, which is about this. Any questions on that? That's important. And when I'm planning, if I do this on your final or exam, I'm not going to make it subjective, right? I'm not going to have you say, oh, what is this compared to this number? Am I looking at this right? I might have 3 to 4 different friction factors set on this axis, and then you just have to pick the right one that's closest. So that means you don't get a little bit off number, kind of. So, okay? Okay, so for a Moody chart, right, our friction factor is equal to 0.038. Okay, so now you plug everything in for HL major. Okay, so let's just do it. 8L, so that's why I underline these, over D. This one I don't have to convert, right, because these inches will cancel anyways. You can convert them both to feet, but it'll be the same. Okay. Velocity. Velocity times 2 gravity. Okay, so it's just me using this equation, plugging everything that we now have. I'll leave those check marks like that. Into here. So what I calculated for HL major is equal to 0.569 feet of head loss. Okay, that's just plugging and chugging. Hopefully that's okay with everybody. Sorry. Okay. So now we have to get HL minor now, right? So that we can compare the two and have an answer for your boss. Okay, that's good. Okay, so HL minor, right? That was equal to your KL loss coefficient, KL squared over 2G. Right, but if your velocity is constant throughout all the features, which we only have one velocity anyways, right? You can actually take the sum of KL if there's multiple KLs. If velocity happens to not be the same, right, you'd have to do this for each different velocity. But you can just do sum of KL here as a shortcut. Okay, so now we have to go, let's go look back at our problem so we can see the features. Right, okay. So let's point out, what do we got? We got a 90-degree threaded elbow here, here. We have a T here, and we have a reducer here. This we don't really bother for. We ignore this part, just for the sake of this problem. There's valves, I believe, in your KL table. You could add if you really wanted, but for our problem, we're just ignoring this. We're just focusing on this upper portion. Okay, so I'll just write here the features that we have that we're going to look for. So we have the 90-degree elbow. Might be too long. Move it over here. Okay, and then we have the T. And then we have the reducer. Let's move that down a little bit. Okay. Alrighty. So let's go through the 90-degree elbow. Where do we find that?
The table.
The table, yes. Right here. So 90-degree threaded is 1.5. The T is already here, so I showed you here. Branch flow threaded is 2. Okay? Yes?
So let's say we have different velocities, we just do each equation for each feature, right?
Right, so if you had different velocities, you would have, your KL with a V. Yeah. So V1, right, then you'll have KL, maybe this is KL1, KL2, V2 squared, 2G, and so on, right? You can only do the summation if the velocity is the same. Good question. Okay, so going back to this, 90-degree threaded is 1.5 for KL. The T is 2.0, right? So let's write that now. So if we sum KL, right, we're going to do 2 times 1.5, because there's 2 elbows. That is ugly 5. Make it neat. Okay, and the T is 2, right? So yeah, that's 2. Okay, reducer. So this one we haven't done yet, but anyone have ideas from past lectures? Oh, never mind, I already showed it here.
The chart.
Yep, this chart. Right, so you have an area going from a bigger area to a smaller area, right? So this is the one that we're going to use. If you need this table for an exam, I will provide this for you, okay? So I'll just do it to the side here. A2 over A1 is equal to D2 over D1. We need to square everything, right? I think it's 0.75 and 0.6.
Yep.
Yeah. D1 is 0.75. I can write the units, but this becomes unitless. Sure, we'll just write it. So this becomes 0.64, which is right here. Okay, you go up, follow the curve, follow it all the way over here, and you get a 0.15 for KL. Man, my 5s are not doing good today. 0.15. Okay, and then let's not forget our velocity squared divided by 2g, right? So that's just going to be 6.52. Man, why did I make this so high? Squared divided by 2 times 32.2 feet per second squared. Sorry, that looks a little weird. Okay, so this is just sum of KL, which is this, V squared divided by 2G. Yeah?
Don't we need to use a velocity coming out of the 0.6 hole since it uses V2?
Yeah, so that kind of goes back to Henry's point too. For this problem, we're assuming just one velocity, so it's easier. But yeah, that is a good point. If you wanted to be a bit more accurate, just more work. So that goes back to Ayad's question too, right? You would just have to do that over there as well. So it's just a lot more work. But yes, that's a good point. Yeah.
On the final, could we just write an assumption and then do something?
Yes. If it comes to that, I solve all of them first to make sure that if there's anything that can run into that's a problem, I will make the assumption for you or state your constants. So I'll try to make things clear. Yeah. Yes, you can do that. It's just more work. For the sake of simplicity, this is how we're doing it. Okay, let's go back to the problem. Okay. So now you plug everything in. You get HL minor is equal to 3.39, this is what I got, 95 feet. Okay. So now we can compare, right? So head loss minor is bigger than major. So this means, right, that you are losing more energy, because this is the energy it takes to overcome this, at the fittings compared to the friction in the pipe. And to see this better, you can do a ratio. Major minor. If you divide these two numbers, you're going to get 16.7%. So this is the percent of loss due to straight pipe friction. Okay, so right, 16.7% is not that big, okay? So you basically disagree with your boss, right? Disagree. Right, and for the exams, I'm not going to have this subjective of a question. I'm leaning towards more of a box your answer question. But this is just for concept-wise to see the difference between your head loss major and minor. So right, because it says your boss suggests that the friction losses in the straight pipe sections are negligible compared to the losses in the elbows. So, right, so this is the percent loss in the straight pipe. The rest is the minor fittings. So you disagree with your boss. Okay, that's it. Is there any questions? Yes.
Could you go back to the KL chart?
Yep. Which one?
The one where you found the T.
This one or this one?
The one right before that.
This one? Yep.
Did you get the T from the branch flow threaded?
Yes.
How do you know it's that one?
I picked that one because the problem said threaded, and the only other two is line flow or branch flow. Branch flow is right when you branch from one section to two. Since we have a T here, it's branching. So that's why it's branch flow threaded.
And then why isn't it like, I feel like if I was doing this, I would look at the pictures below that, which look very similar to what we're doing, and I would try to use one of those. What are those?
Yeah, I don't know why.
Or are the pictures offset?
Yeah, it looks like they're offset. So my e-textbook might be off. Yeah. So for your quiz that I already wrote, maybe it's like giving a little hint, I changed the wording in the problem, so it's word for word what you see on the table. So there will be no confusion once you see a problem on there. That's a good point. There's a little offset, looks like. At least, yeah, this should be up here. And then this should be up here. Yeah, and that's there.
Picture the T's in this specific problem. It looks like the flow is, like you were talking about with the branch flow, it's not going through both sides, it's just one side. So
That is true too, yep. But yeah, but we are ignoring that valve at the bottom, or else we would have put that KL in there too. Good question? Okay, are we? Okay, I think I'll just go like this and they can pause if they want. I think a lot of people are here because we have the project thing, so. Okay. For anyone that's sick at home, here you go. Happy birthday. Alrighty. Okay. Okay, we're almost done. We'll do presentations. What time is it? Very good, very good. Very good. Oh, I hope my audio didn't cut out. If it did, oh well, we can't go back now. Okay, other equations needed for homework 7. So I went through your homework, and here are some that you will probably need. And I'd write these down because if I pick one of these for your quiz, right, you're gonna need them. So we went over kind of these in a previous lecture for turbine and pump head, but here's kind of just restating it. So turbine head is H subscript T equals to capital P, which is power, divided by gamma Q, which is specific weight times your volumetric rate, right? And then to go more specific, gamma is equal to rho times G, and Q is equal to VA if you need it, right? Same thing for pump head, right? So you have the same equation basically, just different subscript. And then I made a note here, because I went through the homework, pay attention to, in the solutions and when you try it, where these are added to your Bernoulli's equation. So if it's kind of taking, power out, it's probably going to be on the right-hand side of the equation. Compared to putting power in, it might be on the left-hand side. So just note where they put that. And then you're going to need this equation as well. This comes from ideal gas law. This is pressure equals density times the R constant times temperature. I will talk about how I feel about that problem at the end of class when I talk about quiz 7. But I'm just saying if you go through the problem, you're going to need this equation as well. We went through ideal gas law, I think lecture 1, right? Okay, so we went over these, but I'm just kind of restating it for your convenience for the homework. So we did not go through multiple pipe system examples, kind of if you were to have a branching flow. We kind of did for this, but we didn't really do a Bernoulli's for it. If you have a flow in series or in parallel, right? Pipes in series and parallel. There's one on your homework. Just for the sake of time, I thought it's not that hard to figure out because you're just using your linking equations that I showed you, right? So I stated your pipes in parallel equation, pipes in series, and loop systems. So you basically just do your Bernoulli's equation, and then you use those linking equations to apply to that problem. So I think you guys should be able to figure those out. If there's questions, you can let me know, but they're pretty straightforward, and you have the solutions, right? So this is everything you should need to solve homework 7, and I will talk about the quiz of what to kind of expect at the end of class, because I want to get through presentations. Okay? Okay, awesome. I was going to do course evaluations next, but I wanted to get through projects first. So let's do like a quick 5-minute break. Which group is presenting first? Feel free to come up. Yeah, come up, and we'll get started. And that question thing I was saying last class, if someone's asking questions, I wouldn't worry about it too much. But if there's no question, right, it's the group ahead of you asking. Is that what I said last time? So you're group number 2, so that means 3 is going to ask for group 2, if no one else asks questions. But I think we did a great job, somebody asking something. Okay, so your group, come get ready, 5-minute break, and we're going to get started right away. Thank you for watching. Bye, everybody.